Okay, so I would try to summarize quickly. So in first three classes, what we have done in the RAC. First class we started with the basics of refrigeration, and then saw the Carnot refrigeration, ideal refrigeration cycle, and solved the few problems based on the refrigerator. Then the heat pump coupled with the refrigerator, then that problem we solved. And after that it comes to the vapor compression refrigeration system, and there we have seen first the components of the refrigeration system, and then we have seen the volumetric efficiency, and why it is required, and effect of various process parameters on the performance of the VCRS cycle, and then regenerative heat exchanger in the vapor compression refrigeration system, and also we solved the one numerical in the last class. After that, this is cascade system. What is the requirement of cascade system? Can anyone tell why it is required?
To make the large pressure differences.
If we requires a refrigeration cycle working in the large temperature difference, right? We can why we cannot do in one go?
Volumetric efficiency decreases drastically.
Because it depends on the pressure difference, so pressure difference would be more than volumetric efficiency. We saw here it is the function of pressure ratio P2 by P1, so volumetric efficiency will decrease. Then today we will try to solve we will be solving one question on the cascade system. Okay, so in the last class mostly we solved the question based on the VCRS, and various types of the problem we solved there, right? If any problem regarding the last class, you can ask me or no, otherwise I will proceed for today. This problem you have done, this I think I have given for homework, right?
Yes. So problem is done, but theoretical piston displacement not under standards.
Where? No. I think this we have solved here, right? I haven't did here. Huh? Okay. So this problem we have to solve today, right? Theoretical piston displacement, nothing. You have to find the length L. Okay. Hello?
Yes, sir.
Am I audible or not? Here we found this D and L found, right? This problem. Is it visible?
Yes, sir.
In this problem, 1 minute. In this problem, this is a regenerative heat exchanger coupled in the VCRS. So there we have found the power required to run the system and the cylinder dimensions. How we found the cylinder dimensions? Just here we took what we have took assumption. Volumetric efficiency is 1, right? This C. So here we have took this one, and m dot we have found, and this is the specific volume at the inlet of compressor, and relation between the diameter and the L is given. So we have found that the D, and with that relation we have found the L, right? Same way here, for the first problem you have to take volumetric efficiency as 1. Okay. Hello.
Yes, sir.
And here clearance volume is the 3% of stroke volume. Means, what is the meaning of this?
Clearance ratio, sir. C.
Clearance ratio C is given, right? What is the C?
This is the yes.
Right? So have you found the which question anyone solved this problem? Anyone tried? Can you raise hand? Okay. So answer, anyone have found anything?
Yes, sir.
Okay, so first part you have to take the volumetric efficiency as 1, and in second part you have to take the volumetric efficiency as you have to find the volumetric efficiency first, because first question is that only, and then you have to proceed, right? Similar way. So okay, should I do this problem or you will try, because it's same problem here what we have did.
We will try, sir.
Uh, I think
We will try, sir.
your doubt is here, what is the theoretical displacement, right?
Yes, sir.
For that, in the theoretical means volumetric efficiency, if you are taking as 1, then that is the theoretical case. Means ideally you are looking for that, but that won't never be that is going to never to be possible. Huh? So
Sir, refrigeration effect per kg means, sir?
means like for the unit mass. Similarly, simply like this is, if this is the cycle. Let's suppose this is 1 and this is 4, 2, 3. Then you are simply H1 minus H4. Means mass flow rate you are taking as 1. Okay. Hello.
Okay.
So I think that's why
Sir,
I
I
am not
have
solving.
one doubt, sir. Sir, specific value at S2 and SG is same
Specific volume at H1.
as at 2 and SG at temperature 30.
Here you are saying.
Yes, sir.
Why it won't be same?
Uh,
Some
then
you are
how?
saying specific volume at this point. Let's suppose we are saying at A, and this is 2. Okay. You are saying specific volume at A equal to specific volume at 2, right?
Yes, sir.
Why it would be? It is what,
Then,
which process
sir,
is? This is the constant pressure process, right?
yes, sir.
So in the constant pressure process, you would be knowing the specific volume at this place, right?
Yes, sir.
And you would be knowing the temperature of this place or not.
Yes, sir.
So for the constant pressure process, V is directly proportional to temperature, right?
Yes, sir. Yes.
So V at A by V at 2 is equal to temperature at A and temperature at 2, right?
Yes, sir.
So you would be knowing this, and this. So V2 you can find, right?
Okay, sir. Okay. Yes.
Like, why you needed this?
Displacement volumetric efficiency and for dimension D and L.
You would be requiring this now at the inlet of compressor. Okay, some here they would have given like some superheating. Okay, okay. Because here superheated gas in evaporator is so superheating is there, right? -5.
Yes, sir.
This graph
Yes.
would be here. So there you would be requiring. Okay.
Yes, sir.
Okay, so we would be starting for today. This question I want to try to you will try. It would be better, and at the end of class I will let you know the answer for all this. Hmm? If you will try, then it would be better, I think, because same problem I have did last time.
Okay, sir.
Hmm.
Sir, can you give the answer for this?
Okay, I need to actually see answer for them, so I will see and let you know. Okay.
Thank you.
Okay, so try this problem. I will wait for 2 minutes, and then I will start. Is there anyone who cannot able to start this problem? Can raise hand. So I will start accordingly. Okay, so we will be starting. So a refrigerant operating on a simple VCRS cycle having COP of 6.5. So TS. What is the simple VCRS? Can anyone tell? Hello?
Dry saturated vapor leaving the evaporator.
So evaporator exit would be the dry saturated. So here it would go. SOP of this cycle is given as 6.5. Anyone got any answer yet? If someone got answer, let me know, okay? The enthalpy of the saturated liquid and saturated vapor refrigerant at the operating condenser temperature of 35 degrees Celsius are this and this. So means this temperature, right? 35 degrees Celsius. H3 is given. What is H3? H3 is this. Anyone? What is the value?
69.55.
69.55 kilojoule per kg. And this value is, let's suppose this point is A. 1 minute. So I will represent 201.5, right?
Sir, is it 334.16 Kelvin?
334. I think it is not. Okay, we'll see. The saturated refrigerant vapor leaving the evaporator having enthalpy is this. Means H1 is given. H1 is 187.53 kilojoule per kg. And what other thing you know? Anyone can tell? Hello?
Yes, sir. H3 code H4.
This is H4. Next, what would be the process? What is the remaining in the whole thing? Only H2 is remaining, right? Hello?
Yes, sir.
So how to find H2? You know the COP of the cycle, and only one thing is H2 is remaining. So what would be the formula of COP for this? H1 minus H4. This is what? Refrigeration effect, right? H1 minus H4. Hello?
Yes, sir.
And compressor input is H2 minus H1. H2 minus H1. Now you know all the data here apart from H2. So 6.5 is equal to 187.53 minus 69.55 divided by, what is H2? Oh, H2 you have to find. H2 minus H1 is, sorry, H1 is 187. 187.53. So what is the H2 from here? Can anyone tell?
205.7, sir. 7 kilojoule per 00, sir.
205.00,
00, sir.
kilojoule per kg. So
Sir, 314.793 is answer.
314, right?
Yes, sir.
314 is correct. So now you know the H2 value. If you know the H2 and this value also you knows. H2 you know and HA you know. And further what is given? Specific heat of the vapor refrigerant is this. Then this would be what? Because it is per kg. So Cp delta T, right, is equal to Cp T2 minus Ta. Is it correct or not?
Yes, sir.
So H2 you know, HA you know, Cp you know, T2 you know, Ta you know, T2 can you find from here? H2 is this, HA is this, Cp is given here, this is the Cp. So T2 is Ta is this 35 degrees Celsius. In Kelvin you can also put. So Ta, what is the value? What is the value of T2 from here? Can you have anyone calculated it?
314.793.
Degree Celsius first tell, because we are going to put this in degree. Either you are putting in Kelvin, then Kelvin you can get.
314, sir. Kelvin.
4.8 I think, yeah. 0.8 Kelvin. So any like if someone is not able to get how we are proceeding it, I think this is simple problem. So this way only problem is going to come. Okay. Is it clear to everyone?
Yes, sir.
If anyone is having doubt, let me know. Okay. So should I go to next problem?
Yes, sir.
So this question is based on the cascade refrigeration system. I initially told like what is the cascade system, why it is required. So first read this problem and then we'll start. So not I will then start. First let me know what is the which system is at the lower temperature and which system will work at higher temperature. That let me know. Okay. And this cycle is this table is for the CO2. Just read the problem. Is there anyone who don't know what is the cascade system? Then I will repeat it. Then we'll solve. Otherwise, this question will make no sense to him. Everyone knows cascade.
One time explain it, sir.
I will explain what is the cascade refrigeration system. Then you try to solve this problem. Okay? 5 minutes it will take. Because otherwise, it is very difficult to solve it. So first thing, volumetric efficiency. What is volumetric efficiency? 1 minus C P2 by P1 to the power 1 by N minus 1. This C is the this compression ratio, this clearance ratio Vc by Vs, and P2 by P1 is the pressure ratio. Pressure ratio is what? Means P1 is the lower pressure and P2 is the higher pressure. Is to the power of 1 by N. N is the polytropic constant. If it is the isentropic process, then it would be gamma. So this P2 by P1 for our VCRS would be the condenser pressure and the evaporator pressure. Okay. Now keep this volumetric efficiency formula in mind. What is the meaning of this volumetric efficiency? Meaning is this: if it is the ratio of the actually volume sucked volume of the compressor that is sucked and related to the theoretically it is possible. So why this is less, that I explained here, because due to the at the end of exhaust there is a higher pressure related to the suction pressure. So suction would not happen until the this internal pressure is less than the suction pressure. So if initially it is more, here more, outer is less, so it is not possible to come new charge here. So it will go keep on decreasing, keep on going through its length. When it will go, this pressure will decrease, and again from here suction will here, then it will start coming. So let's suppose it will start coming from here, then this much volume is not sucked. So in his actual suction is this much only now, and from here to here actually this much is now would be at the suction, and theoretically is this one, theoretically it should be. But so in this way, because here less volume has been sucked, so volumetric efficiency will come into the picture. Now what will happen if if we requires to make a cooling system uh, between very large temperature difference, let's suppose from minus 50 degrees Celsius to um, 40 degrees Celsius. So it is large temperature difference. If you have seen the, if in the problem you would have seen the in the table saturation pressure where you have given here, let's suppose here you can see minus 10 degrees Celsius, approximate 3 bar pressure is there. At 30 degrees Celsius, 13 14 bar approximately is there. So if you take the ratio close to 4, it will come. And when this temperature would go to minus 40 degrees Celsius, then this pressure would reach to 0.5 bar. Then this pressure would be very high, this ratio. And in the volumetric efficiency, you have to put the ratio of that. And then volumetric efficiency will decrease drastically. And at some time will come when volumetric efficiency would be even zero. So that we don't want, otherwise our system will work, no cooling would be there. Now it is clear why we need so in order to do that, we will divide our system in two phases. One minus 42, let's suppose minus 10 degrees Celsius, and then 10 minus 5 degrees Celsius to 40 degrees Celsius. Two parts will do the refrigeration. Is it clear?
Yes.
Not clear, I will repeat some important part again. If somewhere anyone having doubt, let me know, then we'll start that problem. So here simple, we are dividing a one refrigeration system to two refrigeration system. One from minus 42, let's suppose 10 degrees minus 10 degrees Celsius, and minus 10 degrees Celsius to 40 degrees Celsius. Okay, instead of going minus 42 plus 40. Clear? Is it clear to everyone? Hello.
Okay, sir.
So now okay, and keep this formula in your hand. In the now take the screenshot of it. If you are remembering it, then it's very good. If not, then keep this in screenshot of that. Because what is the COP of overall system? COP of overall cascading system is COP of 1 into COP of 2 divided by 1 plus COP of 1 plus COP of 2. So what is COP of 1 and COP of 2? COP of 1 is the refrigeration effect at the lower temperature and work given to that pump, and the COP of system 2 is refrigeration effect at higher temperature to the work given of that pump, that system. So this is COP of 1 and COP of 2. Okay. So can you try this question? Just first read. Let me know what is the what would the refrigerant at lower temperature and what would the refrigerant at higher temperature. Just let me know that thing, then we'll start. Okay. Can you try, or will you try, or should I start?
At lower temperature, it is ammonia, and at higher temperature, it is CO2.
Sure.
Yes, sir.
Just read again. Oh, sorry. It is minus 7.
Now it is reversed, sir.
Hmm. Okay, so you are saying at the
lower temperature it is CO2, then
sorry, CO2 and higher ammonia, right?
yes sir.
Okay. So okay, I will start. You will also solve simultaneously. So in cascade system, let's suppose we are dividing it in two parts. One is this. So what is given? A cascade refrigeration system of 100 TR capacity uses ammonia and CO2. Evaporating and condensing temperature of CO2 are minus 40 degrees Celsius and 5 degrees Celsius. So this data, if it is not given like it is data of CO2, then you can get from here. Evaporator temperature of ammonia is minus 7 degrees Celsius. Power given to ammonia compressor. From here we have decided like at lower temperature CO2 will be there and at higher temperature ammonia would be there. How we have decided? Here it is given evaporating and condensing temperature of CO2 is, what is the evaporating temperature of CO2? Minus 40 degrees Celsius, right? And here it is given evaporating temperature of ammonia is minus 7 degrees Celsius. So who would work at lower temperature? CO2, right? Hello.
Yes, sir.
So this system would be, lower system would be of CO2 and upper system would be of ammonia. It is required to know which system is which one. Why? Because it is given power given to the ammonia compressor. If you don't know which is ammonia, which CO2, then which compressor you would going to give this power. So now we have sure like the power would be given to this compressor. It is 96.5 kilowatt. Both CO2 and ammonia cycle are simple VCRS. Now, okay. So this temperature would be the minus 40 degrees Celsius. So mass flow rate of CO2 we have to find and COP of the refrigeration system, whole refrigeration system we have to find. So will you try or should I start? If you want to try, then I can give 2 minutes and then I will start.
सर ट्राई कर रहे हैं.
Okay, so 2 minutes I will wait and then will start. Just a simple VCRS you have to make and try to find. And I will give one hint. Try with the CO2, taking CO2 system first and then start. Okay. So let's suppose we are making the VCRS cycle for CO2 first. So this cycle would be simple VCRS. So simple VCRS would be of this shape. Sorry. This is 1, 2, 3, 4. So what is the H1? Anyone, what would be the value of H1?
652.8.
Okay. H3 we will be knowing. What is H3 and H4? 330.
431.
Huh? Oh, sorry. It would be the 431, right? So H2 is remaining. How will you find H2? First you have to find the temperature H at 2, means S1 is equal to S2 is equal to what? What is S1? 5.2262, right?
0.2262.
So Cp of vapor is given for CO2 is 0.85. See, is it clear to everyone how I am doing this? I don't think I have to repeat all formula each time. So it is simply 1 minute.
278.
So this is the entropy at point 2. So entropy difference of this, let's suppose this is A point. What would be the S2 minus SA? It would be
AP ln
Cp of V ln
T2 by TA.
TA. So here SA you are knowing, SA would be this value, right? Sg at 5 degrees Celsius would be the SA. So S2 you knows, S2 is this, SA is this, Cp 0.85 and TA would be what? 278, right? Kelvin. So can you let me know what is the T2 from here?
29.72 degrees Celsius.
In Kelvin, let me know.
302.72.
302.72 Kelvin, right? Is it
Yes,
correct?
sir.
Anyone can just confirm? Mm, okay. So what would be the value of H2? Now temperature at 2 you know, temperature at A you know, this is A, and Cp you knows. So can you let me know? H2 minus Ha would be Cp of V into T2 minus Ta, right? So everything you know, what would be the value of H2 from here? Ha you know, Ha would be this, this 649.8 would be the Ha, and CPV is 0.85, T2 is this, and TA is uh, this 5 degree 278. So what is H2 from here?
So T2 361 sir kelvins.
Oh, T2 is 361.
Sir, I have a doubt, sir.
Yeah.
Sir, CO2 is going to work between minus 40 degrees Celsius to
5
5
degree.
degrees, and then ammonia will work from.
Minus 7 to some other temperature. So this temperature difference is because we want to transfer heat transfer from where to where take place, higher temperature to lower temperature, right?
Yes.
So let's suppose this is minus 40 and this would be the 5 degrees Celsius, right? But here it is minus 7. Now what we want? We want simultaneously this heat transfer, whatever heat is coming here. Let's suppose this is Q1 and from here we are going to give W Q1 of, let's suppose CO2. So this is W of CO2. Now here Q2 of CO2 would be there, right? Q2 of CO2 would be the Q1 plus W. So this heat should be transferred to the another refrigeration system without any external something. So how it will happen? So it should go from higher temperature to lower temperature, right? Hello?
Yes, sir.
So now it will go automatically, because, right? From here it is 5 degrees Celsius, here minus 7. So at minus 7 it automatically it will take all heat from here, right? Getting or not getting?
I thought it is working that minus 40 degrees Celsius below, in between minus 7 and at top 5 degrees Celsius.
No, 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 not like that. One system would work and finish here, and it whatever heat at the exit of this, that will give heat to it, and it will transfer to this. Okay, so here temperature would be like 50 60 degrees Celsius, anything, because that data we are not requiring, so that's why it is not given. So if it would be like minus 40 to 5 degrees Celsius, then one system is okay. Okay, then one cycle is more than sufficient. Here this like temperature range is very high, then we are going for the cascading system. Is it clear or not?
Okay, sir.
So can you anyone see this, because it would be wrong otherwise.
सर इतना ही आ रहा है.
Someone is saying 361 or so. So who told what is the value?
Sorry, SM is 5.0037, sir.
SA, no. SA would be, yeah, SA would be this 5.0037. 1 minute, I will calculate.
Yes, sir. 361.1834.
What is T2?
361.1834.
You put here. Oh, sorry. So when you will put here, then what is S2? Anyone calculated H2?
$720.506. 506.
You see, now we know H1, H2, H3, H4, everything. Then B part we will solve first. COP. No, sorry. Now, what is the Q1? Here, what you know? Q1 or what? This 100 TR is what? Can anyone tell?
Q1 sir.
This is Q1, right? So, what is the Q1? 100 TR. TR you will convert to the kilowatt. What? How much it would be? In 1 TR, how much kilowatt is?
351.67 kilowatt.
So it would be 351.67 kilowatts, right? Because 1 TR is equal to 3.5167 kilowatts, right? So it will come this much. Now you know the Q1, and do you know work input to the compressor for the CO2? Knows or no? Don't know.
Don't know sir.
How we can we calculate?
M into H2 minus H1.
What?
M into H2 minus H1.
Okay, that way also you can calculate. Okay, that way also you can calculate, and one more thing, you can find COP of the system first, this first system, because here you know everything, right? So COP of the first system, COP of CO2. What will be the COP of CO2 system? It would be H2 minus, sorry, H1 minus. COP would be the H1 minus H4 . divided by H2 minus H1. So can you get COP from here? Hello.
3.27, sir.
$3.27, huh? Can anyone confirm, is it same?
Yes, sir. Same.
So you know the COP for this system. Then you know the refrigeration effect. Refrigeration effect is how much? This one, right? For the CO2. So you can get the work. What is the COP formula in general? Refrigeration effect by work input, right? So can you get work input from here? What would be the work input? 351.67 by 3.27. Sorry. So can you let me know this value? How much kilowatt it will come? How much?
107.35.
107.35. Is it same for everyone? 1 minute.
Sir, if we calculate COP with the help of temperature limits, then will it be true, sir?
1 minute. Yeah, now tell what are you saying?
Sir, if we calculate COP with the help of temperature limits, that is 5 degree and minus 40 degree Celsius, then sir, मतलब उसको use करके सही रहेगा क्या?
No, but here it is not written. It is the that cannot refrigerator, yeah, ideal refrigerator. Where it is written?
Okay, sir.
It is VCRS cycle, na? It is written here. Simple VCRS. That
Okay, sir.
that formula will work for the ideal refrigeration cycle or cannot reverse cannot, right? Hello.
Okay, sir. Okay, sir.
So is it clear till here?
Yes, sir.
So can you now what is the value of Q2? What would be the Q2 for CO2? It would be the Q1 plus W of CO2, right? From first law of thermodynamics, whatever come to here, work we are going to give, both will merge and go here, right? Same thing happens in the refrigerator or heat pump. Simple problem, right? What is the value of Q2?
459.02.
459.02
Yeah.
kilowatt, right? So this heat would be transferred to this system now, right? This would be the refrigeration effect for this now. Is it clear?
Yes, sir.
Is it clear to everyone? Hello? Hello?
Yes, sir. Clear.
Sir, it's clear.
Okay. So, okay, here I left this. Mass flow rate of CO2. Mass flow rate of CO2, how can you calculate? You know the refrigeration effect in kilowatts, and you can also find the per kg. What is the refrigeration effect here? So per kg, how can you find H1 minus H4? What is H1? H1 is this, H4 is this. So if you subtract it, whatever will come, that would be the refrigeration effect per kg, right? So can you let me know what is mass flow rate of CO2? M dot of CO2. It would be the refrigeration effect divided by H1 minus H4. Correct or not? Hello?
1.585
1.585
kg per second.
kilogram per second. So first problem is nothing, it is simpler one. So it would be happen this way. So now coming to the second part. So heat rejection from the first refrigerator of CO2 would be the evaporator refrigerating effect for the NH3 ammonia. Is it clear to everyone? This is the most important thing for the cascading refrigeration system. Okay. This one only keep you in mind. So now you would know the refrigeration effect for this system. Work input you know. So can you let me know this? Otherwise it is not necessary here. You can find the COP of the ammonia system. Because here in second part only you have to find the COP of the whole refrigeration system. So COP of ammonia system is what? It would be the Q1 of ammonia divided by W of ammonia. Q1 of ammonia is what? This is the Q1 for ammonia 459.02 and the work for ammonia is what? Ammonia compressor 96.5. So what is the COP?
4.7567.
4.7567. 75 na? This one, right?
Yes, sir.
Okay. So now you know the COP for both systems. COP of CO2 system. What is the COP of CO2 system? Value can you let me know?
$3.276.
How much? 3.276.
276.
Okay. And what is the COP of the ammonia system?
4.758.
4.75.
756.
756. Oh.
756.
Yes.
Okay. So can anyone remember the formula? What is the COP of overall system?
COP of 1 into COP of 2 by 2 plus COP of 1 plus 1 into 2.
So what is this? COP of
NH3,
NH3
COP of CO2,
into COP of then
1 plus
upon 1 plus
COP of NH3 into COP of CO2.
COP of NH3 plus or into?
Plus, sir.
Plus na? COP of CO2. So
CO2.
put all these two value here and let me know the COP of overall system.
1.725.
1.725. Right? Right now? Correct? This you can also find in some other way. Can anyone tell me seeing this cycle? Any idea?
Simple Q1 by W in 1 plus W in 2.
So COP of overall system would be, what is the real COP formula? This is the refrigeration effect by energy input. So in this system, how much energy we have given? Two places, right? here W of CO2 and W of NH3, and the refrigeration effect is what? Refrigeration effect is only this Q1 actually, and here we are doing two times because two refrigeration cycles are working. So overall system, if you are going to do the COP, then main refrigeration effect is this only. So in this way, how much it is coming? Can anyone tell?
1.723.
Okay, here W of CO2 plus W of NH3. So when you will find this way, it will close to come. Otherwise, it will mostly it will same 1.723.
Yes, sir.
So COP of overall system. So is it this problem clear to everyone or not?
Yes, sir.
Yes, sir.
Okay. If anyone having any doubt here till now, can let me know. Otherwise, we will be switching to some other topic from today. Any problem till now here? Hello. Okay, so one problem we have done on the cascading system, and one problem on the that regenerative heat exchanger in the VCRS. That one problem we have did. So this problem is actually very important. So if here you don't know clearly like what is the refrigeration effect in regenerative cycle, there you may commit mistake. Lot of places where you can commit. Okay, for what would be the refrigeration effect, what would be the compressor inlet, so that you have to see. So if this you have done, then it is okay, I think. Otherwise, others are simple. So this problem I would give answer to you. 1 minute. So for the refrigeration effect per kg, here I'm writing answer. One a if answer is not matching, then next class we can solve. Okay. 126.74 kilojoule per kg, and mass flow rate of refrigerant in per minute 126.74. Second answer will be 24.9972 kilogram per minute. C would be the theoretical piston displacement. It is coming in liters. So they have volume they have given 2.1879, and COP of the system is
5.72.
5.73. Yeah. And okay, here it is in this way. So dimensions you can also find. I think some relation they have given stroke to bore. So dimensions are the D is 95.33 and L is 140. So in second problem, if when you will take the clearance ratio, then it is coming volumetric. Anyone calculated what is the volumetric efficiency you are getting?
94.26%.
Here it is coming 93 point, sorry, 93.49. So it is okay. Anyone calculated bore and diameter? Have you calculated?
95.18.
Here diameter is coming 97.56 mm, and length is 146.34. Okay, just try it. If it is not matching, 2 or 2 3 mm is okay here and there. Up to 5 mm is also okay, but after that it is coming like 10 mm this much difference, then you have to see. Okay, is it clear to everyone? Should I start something else? Hello.
Yes, sir, it's clear.
Okay, so today we will start the theory of the vapor absorption refrigeration system. We'll do later. So today we will be doing. Can anyone know which refrigeration Breton cycle? Do you know?
Yes, sir, reverse Britain. We know.
What is the Breton cycle? First, that I want to know.
Air
Gas
refrigeration.
turbine from Breton cycle.
What?
Gas turbine works on Breton cycle.
Okay, gas turbine works on the Breton cycle. And which processes are there?
Isentropic
Hmm.
and constant pressure. Isobaric process.
Okay, two processes are at constant pressure and two processes are isentropic. Okay, Breton is okay. Then if it like two isentropic processes are there, but we constant pressure processes we change to the constant volume process. Then which cycle it will become?
Otto.
Okay, if we change both of constant volume process to the constant temperature process, then which cycle it will become?
Carnot cycles.
Not cycle, right? So can anyone know what is Stirling and induction cycle?
सर इनके बारे में नहीं पता.
Okay, so just simply for those cycles you try to find which processes are there. Actually those are not in the syllabus, just those are also 4 processes cycle, so that you have to see. Okay, with two names. Okay, next class I will randomly I will ask these questions. Stirling and Ericsson. More detail of it is not needed. For us only auto, diesel, dual and this Breton, reverse Breton, Carnot and VCRS. These are main cycles. Okay. IC engine is anyone teaching?
No, sir.
Okay. Okay, then the Breton cycle is the two constant pressure processes and two isentropic. So we are in the refrigeration system. So we are going to see the reverse Breton cycle. So what is the application of the reverse Breton cycle?
Air refrigeration cycles.
Applications.
Aircraft.
Can anyone know what is the other name of reverse Breton cycle?
Reversed Joule cycles.
Bell-Coleman.
Bell-Coleman cycle. Okay. So this also you sometimes you say Joule cycle, you sometimes you say Breton cycle. Can anyone tell what is the difference in both? Hmm?
Both are same, sir.
Working fluid का difference है क्या sir?
Okay, just if anyone knows, let me know. Otherwise, I will tell. Working
Breton
is
cycle
same
is
and
closed cycle and Joule is open.
what?
Joule is open cycle and Breton is closed.
Joule cycle is open cycle. Here you are taking each time fresh fluid, fresh air, and in Breton cycle same air would be keep on circulating. Okay.
Sir, I don't know about Joule cycles.
Nothing. I will make here. Then you will let you know. I will. You simply like 1 minute. In this you can't get. I will draw that. Breton cycle, you know, right?
Yes, sir.
Okay. So I was in the application. So I will sorry. So when I will be making the block diagram, that time I will let you know which cycle become Joule cycle and which cycle become Breton cycle. That time I will explain. So
Okay.
application of this is the one is the aircraft refrigeration system. And any other application can you let me know? One is the gas liquefaction. Okay. So TS diagram and PV diagram for this will make. What is this process?
Heat absorption.
Q absorption. And what is this process?
Constant pressure heat rejection.
Heat rejection. And here W input, and here some work you will be getting. And when you will make TS, it will become simply
Sir, what is the W input and W output?
here you would be giving some work to compressor, and here you would be getting some work from the turbine. Okay, because here it is air. There in VCRS, and here one, this is the major difference. In VCRS, what you are going to use for the expansion?
Throttle valve.
Throttling valve, right? And in throttling valve, if you okay, one question I will ask again. Here you are using turbine, right?
Yes, sir.
And there in VCRS you are using throttling valve. If you use throttling valve here for the expansion, then what will happen? Question get clear?
Yes, sir. Large size of the total valve required.
No. Why?
Temperature get reduced.
Anyway, you want temperature reduction here, right? Here what is happening? Temperature here is something, this temperature. This is the inlet of expansion valve, right? If let's suppose this is expansion valve, that is then. And here it will come. Try to find this. If you are not getting, let me know. In next class I will let you know. This also think in way of Joule-Thomson coefficient you will get. What is the Joule-Thomson coefficient of air?
0, sir.
0. And here working fluid is what? Working fluid is what?
Air.
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 What is the Joule-Thomson coefficient? dP by dt.
Constant enthalpy.
If Joule-Thomson coefficient is 0, whatever temperature difference you will give. Here what is happening? Here some pressure, higher pressure, pH. Here pH, higher pressure is constant. Here P lower, constant. Now let's suppose here some dP you have given. This pressure change will happen in the throttling valve. But what was the temperature difference there? No temperature difference you would be getting, right? Or I have written opposite, I think. dt by dP this, right?
dt by dt.
It is dt by dP. So whatever it means, you are getting my point. What I want to say here.
Yes, sir. But in VCRs, we liquid refrigerant.
There Joule-Thomson coefficient is negative, so you are getting cooling there. No issue.
Yes, sir. But here only use the.
Here no cooling you will be getting. If you are not getting any cooling, then what is the effect? It will not cool here, right? Getting the things here or not?
Yes, sir.
So this is that is why we are not using expansion valve as throttling valve here. We are using turbine. In turbine, what is the advantage there? That turbine work you can give to this compressor, right? So compressor input is also decreased. And because it is air, in air with a turbine you can get more amount of work. But there it is liquid, in VCRS. So liquid you can't get that much work, right? So that's why we are simply using the expansion valve there, and here we are using turbine because here temperature is pretty much high. So here temperature is approximately 200 degrees Celsius, 250 degrees Celsius, and here where this 4 point is, this is close to 30 degrees Celsius. So very much power we are going to waste if we are going to simply waste it here. If that work we are going to take and give this, then our COP of the system will increase. Is it clear why you are using compressor turbine here in place of this uh, throttling valve? Because these are the main questions, like theoretical question that may come. Okay, am I audible?
Yes, sir. Yes, sir.
So what with the refrigeration effect here? Okay, first I will let you know. This would be the inlet of same cycle is same as VCRS. This is the inlet of evaporator, and this would be the exit of evaporator. This is the inlet of compressor. This is the 2 point would be the exit of the from compressor, and from two would be the in condenser it will go, and 3 exit of condenser, 3 entry of turbine here. There entry of expansion valve or throttling valve. Here inlet of turbine, and 4 is the exit of turbine. Now naming of each is clear or not? I am running a bit fast because it is same as the VCRS.
Will you
Hello.
please repeat once, sir, naming?
Okay. 4. What is the 4 at the VCRS?
Entry to evaporator.
Entry to same. One is also same exit to evaporator, and one is entry to the compressor in both cycle, right?
Yes.
Yes, sir.
And 2 is the exit of the compressor and entry to the condenser. Okay.
Okay, sir.
And 3 is exit to the condenser and entry to the turbine. Entry to the turbine in Breton, and entry to the expansion valve in the
PCRS.
VCRS. And 4 is the exit of the turbine and entry to the
Evaporator.
evaporator. Is it clear now?
Yes.
Okay, then what would be the refrigeration effect now? H1 minus H4. Correct? What would be the WC? WC would be this. What would be the WC?
H2 minus H1.
H2 minus H1. Because it is air, so we can simply write Cp T2 minus T1. Right?
Sir, but in for WC, we will minus turbine work, na?
That will later do one by one. Here Cp T1 minus T4. And what will the WT? WT is this. WT will be H3 minus H4. Cp T3 minus T4. Any doubt till here? No doubt, right? What will be the COP refrigeration effect by WC minus WT? Any doubt till here?
No doubt.
Okay. So now we knows Cp of air, and T1, T2, and T3, T4. Everything we know, and what will be the equation of this compression or expansion? Isentropic we are considering, right? So PV to the power gamma is equal to constant. And here relation between temperature, pressure and volume, anyone can tell?
P1 1 minus gamma. P1 power 1 minus gamma.
1 minute in terms of temperature, okay. P2 by P1 to the power
Gamma minus 1 upon gamma.
Gamma minus 1 by gamma
is equal to
T1 by T2. You say.
is it correct? Is equal to T2 by T1, right?
Yes, sir.
So use this equation in order to, and what would be the P2 by P1 here? This is what, let's suppose this is P2 and this is the P1, okay, because it is constant pressure process. So we are considering P2 by P1 as RP here, pressure ratio of the Breton cycle, okay. So in Breton cycle, sometimes it would be given pressure ratio is this, and entry to the evaporator is at some temperature and this pressure. So automatically this pressure is known, right? Is it clear?
What, sir?
In questions, is it clear? P2 by P1 we are saying as pressure ratio RP. P2 is the
Yes, sir.
P2 is the constant pressure of the condenser or heat exchanger at higher temperature, and P1 is the evaporator pressure or pressure at the lower temperature. So P2 by higher by lower ratio is the pressure ratio. Okay. In questions like pressure ratio would be given to you, and the condition like inlet to the evaporator temperature is 30 degrees Celsius at 1.05 bar. So P1 is given. If RP is given, then P2 is also known to you. Correct?
Yes, sir.
Is it clear to everyone or not?
Yes, sir.
Yes, sir.
So now when you put this refrigeration effect formula here, Cp T1 minus T4, Wc you will put Cp T2 minus T1, Wt put Cp T3 minus T4. When you put the Cp will cancel out, in terms of temperature only it will remain. That temperature will solve and find the in terms of pressure, because Rp we are knowing. In terms of pressure ratio, when we will find the COP, what is the formula? Can anyone know? Hello.
Yes, sir.
What is the formula?
1 by RP power gamma minus 1 by gamma minus 1. RP power gamma minus 1 by gamma minus 1.
Let's suppose we are saying x is equal to gamma minus 1 over gamma. So, okay, no, if you will say, then it will come 1 by r to the power rp to the power x by minus 1. That you remember anyhow. Because this ratio you can remember from here. Rp to the power gamma minus 1 over gamma, right? Same thing. If you know the temperature limits, then simply 1 by T2 by T1, right? Same, T2 by T1 is equal to the this. Correct or not? Getting what I'm saying? Like this temperature T2 and this temperature T1 you know, then directly you can write this. Are you getting or not?
Sir, that formula for COP 1 minus 1 upon RP raised to that term is for COP of Brayton cycle.
COP of Brayton cycle is, that's 1 minute. Okay, this is a gamma minus 1 over gamma. This is power actually. So this is not working properly today.
I was asking, sir, the COP of Brayton cycle and the COP of reverse Brayton cycle are different.
No, COP of Brayton cycle. Brayton cycle is what? Brayton cycle is a work producing cycle, right?
Yes, sir.
So why there you are going to find COP?
Okay, sir. Got it, sir. It is efficiency, sir.
There you will find efficiency, no? RP to the power x it would be here, right? So this is the theoretical, right? Now, actually, what will happen? One example I will tell, and then we'll stop for today. Next class will solve the problem on this. Let's suppose these are the process. This is 1, 2, 3, 4. Now, if you do the real process, it is the ideal one. Here, efficiency you can COP you can find 1 by RP to the power x minus 1. Now, what will happen? Some compressor efficiency would be given to you, so it will go this way. Sorry, why did not go this way? So let's suppose this is 2 dash, and here it will go this way, 3 dash. So now 2 dash and 3 dash you have to find, right? It is the real process. In a real process, here they will give like efficiency of the compressor is 0.85. Efficiency of turbine is 0.9. So you will be calculating the temperature of 3 dash and 2 dash. Can you calculate?
Yes, sir.
So those keep in mind, and then we have to do. Also here regeneration will happen. We can be done. So that we'll see how those problems can be there. So those problems we will be doing. Mostly theory of this is done. So one thing I can also make. Let's suppose this is the refrigerated space. Refrigerated space, and from here it will go to the, let's suppose this is the compressor, and actually, okay, from here it will go to the two things you can say, a cooler also you can say, or you can say condenser also, both are okay. Cooler we will say. From here it will take the some Q absorption or refrigeration effect we can say, and here we would be providing some work of compressor, and it will reject heat here. Now after this it will come here, and turbine would be there. Oh, sorry. Okay, this is piston system. Simply it is getting work. Okay, W of turbine. So piston cylinder arrangement I want to show. So we would getting some work. If now after getting turbine, you are exhausting this air to the atmosphere, and here again you are taking new air from the atmosphere. Okay, let's suppose this is surrounding. If you are now after this exhaust this to the surrounding, then it will become which cycle?
Joule cycle.
This time it will become Joule cycle because it is open system. It is not closed cycle. So it will again suck air from the surrounding. It will go absorb heat from the refrigerated space, and it will go to compressor, cooler, and to the turbine. Turbine work will take and exhaust to surrounding. If you are using this same, if working fluid is air only, then we can do this. Let's suppose now working fluid is the argon. Okay, then you cannot reject that argon to atmosphere because argon is somewhat costly. So air is more than sufficient amount, so we can suck again and we can reject it. Because effect of gamma, what is gamma?
Adiabatic index.
Adiabatic exponent, you can say. If this increases, then what would be the effect on COP?
Increases, sir. Gamma increase.
COP will increase. So what is the COP of argon? Sorry, gamma of argon?
1.67.
1.67. So it increases, and for air it is 1.
1.4.
So if argon is working fluid, then we cannot go for the open cycle, and air then we can go. Now it is clear what is Joule cycle, what is Breton. It will become Breton if we will add connect it. Okay.
Okay, sir.
One more thing. That isentropic efficiency formula I'm not writing here, so I think that you can do, right? Here, right? It is required to write the formulas.
Sir, in case of isentropic efficiency of compressor, the curve deviates from 1 to 2 dash. So in case of turbine, it should deviate from 3 to 4 dash.
Oh, sorry. It will go this way, right? 3 to 4 days it will come. Sorry, it is 3 to 4 days. Okay.
Sir, if 4 days is right or left?
Entropy for irreversible process, entropy will always increase. This is one thing keep in mind. Okay. Here entropy is this. Ideally entropy is this, and irreversibly what would be entropy? Entropy of system will increase. So if you will go this way, then entropy of system will decrease, right? So you cannot go this way. This will come this way. Is it clear?
Okay. Yes, sir.
So conceptually you will make. I thought like I'm going this way, so that I made this. So formula I'm not writing. So you can see like what is the ideal. If it is for turbine you are writing, you have to gain work. So irreversibly, if it happens irreversibly, then you are going to get less work, and ideally you are going to get more. So here you can write efficiency of turbine is equal to the actually what you are getting divided by theoretically what you are supposed to get. Here opposite will happen because here you have to give work. Ideally you have to give less work, but now you have to give more work. So that way you can think and do. If any problem is there, then let me know. I will do again. Okay.
Sir,
Yeah.
reversible adiabatic process and isentropic process both are same.
Yeah.
Sir,
But keep one thing in mind. All reversible adiabatic processes are isentropic, but all isentropic processes are not reversible adiabatic process. Getting what I said?
yes, sir. Why, sir?
So actually in thermodynamics I have told that time. Let's suppose what is the total entropy?
Entropy of system plus surrounding.
Entropy of the system and entropy of due to the surrounding. Okay, that you said. I will take. Now take the system only, surrounding leave. So here 1 minute. Okay. So one system I am taking. So let's suppose for this system currently we are going to give some heat to it. Okay. Hello.
Yes, sir.
And here I'm thinking it is internally. Do you know internally reversible? Internally irreversible.
Yes, sir. Due to the molecular friction.
So first I am taking this system is uh, internally reversible. Okay. So what would be the total entropy of system? One is the delta S due to the internal irreversibility. Internal irreversibility I, okay, I will write I internal irreversibility plus uh, Q by T. Q by T, you are getting what is Q by T? This is the due to the interaction of heat with the system. Hello.
Yes, sir.
Now think of system is internally irreversible, but no heat interaction is there. First case. First case is what? Internal. If a system is internally, what I said, internally irreversible. If internally irreversible system would be there, and you know one thing, and now what we are one more case I am saying, it is totally adiabatic system. Okay. Got first case what I told? Adiabatic
Yes.
means Q is 0.
Yes, sir.
And
Only internal
internal
irreversibility exists.
irreversibility would be there. If internal irreversibility is there, means this is more than 0, right? Greater than.
Yes, sir.
So there is some system is having some more than 0 entropy would of system is more than 0. So there also one thing we know, because it is totally insulated, and entropy of universe always increases. So here it is sure, like internal irreversibility would always be more than 0. Correct or not?
Yes, sir.
So this one thing is there. This keep in mind, internal irreversibility would never be less than 0. Now coming to the second case. Second case I am thinking the system is internally irreversible, and heat rejection from the system is there. Got the second case? Delta S of internal irreversible, I am writing IR. Okay. Delta SIR is there, and heat from the system. This is system. So what will be the net delta S of system?
Delta IR
Delta S
minus Q by T.
plus Q by T. dq by, actually it is plus dq by T,
Minus,
but as of now I am writing Q by T. Okay. So let's suppose this
sir,
value is,
minus Q by T, sir. Heat
what?
rejected from the system.
We are considering, okay, sign I will take, but minus Q I will take. Heat rejected by the system is minus of we will take. Okay. Hello.
Yes, sir.
So let's suppose from here what I have derived, it is we are supposing delta S of internally irreversible is positive. Let's suppose this is 0.01. Okay. And now heat rejection from the system means it is negative, minus Q, right?
Yes, sir.
So let's suppose this is our body at constant temperature, thermal reservoir I am taking it. Thermal reservoir, if we will take, then some heat, taking some heat out in will not change the temperature of that body, right?
Yes, sir. Yes, sir.
So some heat would be going out, but that heat we will adjust that way, like Q by T would be the minus of 0.01. Got the thing?
Yes.
So what would be the net delta S of system? It would be 0. So this process is also isentropic. Correct or not?
Yes, sir.
And the next case, third case I am taking. Third case is, 1 minute. हेलो. हाँ, 2 मिनट बस आए. कॉल बैक कर. Okay, so what will be the net entropy of the system? If case is it is adiabatic, and reversible adiabatic. Okay, one thing, reversible plus adiabatic. If it is reversible, then what would the delta S of internal irreversibility? It would be 0, correct?
Yes, sir.
And what would be the due to the adiabatic? Q is 0, 0. So it is also isentropic, right? So what statement I have told? If a process is reversible adiabatic, then that would be isentropic, but all isentropic would not be reversible adiabatic. This is the example, right? It is not what I told. It is not adiabatic and not got the thing. It is not adiabatic, right? But it is a isentropic process.
Yes, sir. Okay, sir.
So it is clear, right?
Yes, sir.
Okay. So I think next class I will be doing the problem on the reverse Breton cycle. 5 6 good problem we will do, and then switch to next topic. Okay.
Okay,
If
sir.
any doubt is there, then you can let me know, and I can give my email ID. If any doubt is there, then you can text me there. So if no doubt is there, then we are stopping for today. Oh, 1 minute.
Thank you, sir.
Okay. Thank you.
Sir.
Hello.
Sir.